Hello, it's Robert here, and I'm for Doomsday Debunked, where I help people get scared of various things, and just by looking at the facts. And I just want to explain today about how the greenhouse effect really works for people who are puzzled, baffled by climate change. So, this first of all shows how much of an effect there is. So you can see there, those are the four of the main planets that have got greenhouse effects. It doesn't include Titan. There's Mercury, it's got hardly any. So its temperature is 437, it goes up a little bit. Venus has got a huge one. The temperature would be, if it wasn't for, it would be minus 41 degrees centigrade if it didn't have any atmosphere. It goes all the way up to 462 with the atmosphere. So there's Earth, then average temperature would be minus 18 without the greenhouse effect. If it was just a planet without any atmosphere, it goes up to 15. And then here's Mars, and the temperature would be minus 64 without any greenhouse effect. It gets half the light that Earth does. Remember, it's warming up from very cold temperatures, and it goes to and it's minus 58 with its very small greenhouse effect. So the greenhouse effect does make quite a difference, and this is the total greenhouse effect of the tiny amount of carbon dioxide. You'd hardly believe it would do all that, and the water vapour, and 0.04% carbon dioxide and water vapour are the main things that are doing that. So I want to try and explain why that is. And it doesn't work like a greenhouse. So people think that it works like a greenhouse. They also think that greenhouses keep plants warm because they're made of glass, and they think the glass absorbs heat. But if you look but you can actually, a neat experiment that Robert Wood did in 1909, he made a kind of greenhouse out of polished table salt. Now, table salt wouldn't make a very robust greenhouse, but if you just get a very thin sheet of salt, and he put little glass traps underneath it, put a little trap underneath it, and he compared that with a sheet of glass. And it didn't make any difference. It will reach almost exactly the same temperature whether it was covered with glass, which traps heat, or covered with the salt, which is just completely transparent to infrared. And so a normal greenhouse, all it does really is to stop you get the warm air, the sunlight heats up the air inside the greenhouse, and then normally they would just go up, warm air rises. So a normal greenhouse just traps the air and stops it going up. That's all it does. That's all it does to keep it warm. So if you're a polytunnel or something, then it's just keeping the air gets warmed in the daytime, and normally at night it would just spread out into the atmosphere, and that's what keeps it warm, and keeps it warm in the daytime as well. That's all the greenhouse is. So the greenhouse effect doesn't work like that. It's not trapping heat in that way. It's not stopping convection. This convection happens perfectly fine. So what it does is rather unintuitive until you get used to it. So this is explaining the whole thing. Now, so this is the surface, and that's the greenhouse layer. And if you had the kind of intuitive idea, you'd think greenhouse layer should be hotter than the surface, probably, or the same temperature. Actually, the only way the greenhouse effect can warm the planet up is the greenhouse layer has to be much colder than the surface. The colder it is, the more it's warming it up. It's a bit unintuitive. And so here this is a very simple model. We only have one layer of greenhouse layer in the atmosphere. You have the sun coming down, warms up the surface, goes up to the atmosphere, some of it goes down, some goes up. And you can see he did this little model, computer model of it, and you can see the surface temperature is goes quite high, and the atmosphere temperature is much lower. That is the layer in the greenhouse layer of his atmosphere. It's a very simple toy thing. Now, this is an even simpler version, which really shows how does it work. And this is a planet that hasn't got any sun. So all you've got, and that's roughly, maybe a little bit less, roughly what the Earth's the Earth produces by way of warmth as a result of the sunlight coming in and then it emitting it again. But suppose it just emitted it, it's just the Earth was naturally warm. So the Earth is naturally warm to a certain extent anyway. But suppose it was just naturally warm to that extent, so you didn't even need the sun to keep it warm. There's a lot of, it could be a very young planet. So when planets are very young, they start off just molten, of course, and then they slowly get cooler and cooler. So imagine Earth was a young planet, but it's solidified, but still got a lot of internal warmth. Now, put around it, as your greenhouse layer, a totally non-transparent steel greenhouse, just a like Trantor, if you know your Asimov. This is a kind of steel-covered, just an entire city as a planet, and then it's got a layer of steel above it as a kind of roof, and the people walk around in between the two. And then he actually has lots of buildings in between, but just suppose there's nothing in between. And then you just, for it simple, you've got a vacuum in between. So there's no complicated air or anything. So you've just got a steel planet and a steel roof. And now let's just paint them all a matte black. So they just work like it's called a black body. It's the simplest kind of thing that you have. It just absorbs and emits any light that comes in, it absorbs, and then anything, and then it just emits everything again. And so if you had a situation like that, they're both black bodies, and this is just radiating out. It's only producing 235, but then you've got your shell around it, and it'll come into equilibrium with the shell producing 230, reaching that temperature that this had, because the way you can see that is that whatever, if you didn't have the shell, then that would just be all 235 per square meter. We're supposing these are both, that the gap between the two is so small that actually this is just very schematic, and that should be the same size as that. So with a really very, very thin, very, very narrow gap between the two. So it's the same surface area, and that should be producing 235 watts per square meter if that is. Once they're in equilibrium, and that's just the total amount of heat that's getting to it from the inside. So once it's reached equilibrium, then that should be producing 235 watts per square meter going outwards. It'll be producing the same amount inwards, because it's just a shell, and both sides should be equally warm. And so then if you work out when it's in equilibrium, in order to make it all balance, then this has to produce 470 watts per square meter outwards, in order to be in balance with that extra 235 coming back in. And so you'll end up that this is going to be much, much warmer than that, just to be in balance, because it's producing all its own. It's got to add 235 on top of everything, and then it's got all this heat coming back in again, bounced back from the shell that's around it. So that 235 has to be on top of that, which is warming it up. And it's not unlike the way that if you have a thermos flask and you've got some hot tea inside, so that all sounds very complicated, but if you've got some hot tea inside a thermos flask, the thermos flask feels cool on the outside, and you can intuitively see that if the thermos flask was quite warm, then the tea wouldn't be so hot, because it's losing all its heat, especially once it goes into equilibrium. So the cooler the thermos flask is, the warmer your tea is going to be inside. And so it's quite like that. So you've got to have a cool layer on the outside, and that'll keep the Earth warm. And if you had it like that, I mean just one layer like that, then you can actually work out the temperature. So if you work out the temperature there, it would be minus 19 if it was just if it didn't have the shell. Add this shell, and it goes right up to, and I work it out somewhere down there, right up to 28.58 for 29 degrees. We haven't got a perfect black body shell, and so we're not coming up with the same temperatures as ours, which are only 15 degrees. But that gives the idea. And we've got two shells, or more than that really, but I mean that's the simplification. So if you had a second shell, it warms up even more, and because each shell has that extra increment of the 235. So that's how the greenhouse effect works. And you actually do get, if you had like I was talking, like a young warm planet, and even quite an old planet that's got a little bit of internal heat, and its only temperature is like, if you had an Earth mass planet, and the effective temperature would be 30 K because of long-lived, so it's like the Earth, same age as the Earth, it'd be about 30 degrees above absolute zero. And then above it you have a thick atmosphere of hydrogen, and that's all you've got. And there's no extra heat being added to your planet. It's just very cold at 30 degrees. But if it had 1,000 parts per 1,000 atmospheres, that's very, very thick atmosphere of hydrogen, but not impossible. I mean, it's basically, if you imagine this planet formed where it's very, very cold, way, way out, and it's got, so it could either be a rogue planet or it just formed naturally a long way away from any solar system. And a long way away from its parent solar system, and it just accumulated a lot of hydrogen, very much like a gas giant. Then at the bottom it would be very warm. So you could have an Earth mass planet with great depth of hydrogen, and then you could have an ocean of water brought up to above the freezing point of ice, just by the hydrogen causing a greenhouse effect to come around it. This chap calculated that, and he concludes his letter to Nature by saying that, depending on the assumptions, these could conceivably be the most common sites of life in the universe. This might be the biggest amount of water in our galaxy, could be in these completely unknown planets, be very difficult to spot, way, way out, covered in hydrogen, extremely cold. And it's not impossible that there's more water there than there are on planets like Earth, and there might be quite a lot of life on them. And so those would, if they do exist, and so theoretically they're possible, then they would be warmed up entirely by the greenhouse effect from 30K, which is minus 240 something degrees centigrade. Let's do the conversion in Google. Minus 30K C, if I've done the calculation, minus 303, minus 30K, that puts, no, 30K is not minus 30K, what am I talking about? That's an impossible temperature. Minus 243 degrees centigrade, very, very cold. Oh, and let's put that in Fahrenheit for those of you who need Fahrenheit. Minus 405 degrees Fahrenheit. So that would be its natural temperature, but you could, with enough hydrogen, warm it up by its greenhouse effect all the way up. And if you did that, the outside of the hydrogen from the distance, it would still look as if it was minus 405 degrees Fahrenheit, or whatever it was. So it'd be quite difficult to spot from a distance, because the greenhouse effect is keeping the warmth in by being a very, very cold layer, and then all the warmth is kept beneath, in fact, like there's layers above it. So that's that is how the greenhouse effect works. So it's not happening at ground level, and the only way it can warm up the planet is by making the planet look the same temperature it was before, but it's actually right up in the atmosphere. So it would be minus 19, the surface, but instead you've got this layer right up in the atmosphere that's minus 19, and then it's keeping the surface much, much warmer than that, to this 15 degrees, whatever the temperatures was. So I had the two temperatures there. So we've got this layer up in the atmosphere, which would still be minus 18, and it's making the surface seem like it's 15 degrees, make the surface, warming the surface up to 15 degrees by staying much colder than the surface. So this is, most people just do not know this about the greenhouse effect, and they assume that it's a warm layer. It's a cold layer. It has to be a cold layer in order for the planet to be warmed up. Now, actually, it's more complicated than that. You have two layers of atmosphere. This is still like a Tinker Toy thing. There's two layers of atmosphere. And by the way, I sort of wonder what to do about this, but it's just so nice. It's such a nice idea. And as far as I know, this is standard stuff. The greenhouse. This is exactly what I explained, except that in your idealized greenhouse thing, you have the sunlight coming in and warming it up. And you imagine the atmosphere is completely transparent to the sunlight, which of course it isn't really, but in this idealized greenhouse. then this is very standard. You have this coming in, and then you warm up the surface, then the rest is exactly the same. It's not got internal heat. It's just warmed by the sun through a transparent atmosphere. And then you think it's emitted infrared, and then infrared just works the same way, emitted from there, and then you've got this going both ways, and so you've got coming down, and so you've got to have that be excess over what's coming down. But once it's in equilibrium, it's the same thing. It's just the sun doing heating instead of internal heat. But this chap, and he's contributed to What's Up With That, which is a basic climate denialist. He doesn't think that there really is an anthropogenic greenhouse effect. So, but I wanted to use him because he's just a very nice idea, and I can't find any kind of easy explanation for the general public. So he understands his greenhouse effect well enough. We've got something else that's kind of a little bit strange. I want to go further beyond that. And so anyway, so then you might wonder, how can the infrared be trapped completely when there's hardly any carbon dioxide in the atmosphere? And it's the same with water vapour, because remember, so now I just want to explain there, we're trapped by both greenhouse carbon dioxide and water vapour. Carbon dioxide is very persistent in the atmosphere, and if you add a bit of carbon dioxide and then half of it is gone in 40 years, 15% remains thousands of years, 30,000 years later or something like that. And the reason is that as the planet warms a bit, with carbon dioxide helps it to warm along with water vapour, as the planet warms, then the oceans get less absorbing of carbon dioxide, so it's much harder to go back the way you came than it is to go up. Adding carbon dioxide is much easier than removing it. And so that's basically the main source of our problems, really. Like the carbon dioxide, that some of the carbon dioxide was produced in the early 20th century is still here, and some of what we're producing now will still be here 13,000 years from now. Very different from methane. I mean, if you just sort of halved like methane all the time, then we would have much less. Even by 2100, we'd be down to, so it's 45 years, be a quarter by 90 years. It's more, and 15%. It would be like, it does still make it. It still is rather slow with the way it reduces, but it's even slower because of this being absorbed less in the ocean. The oceans are constantly absorbing carbon dioxide, by the way. They're not emitting carbon dioxide. As they warm up, they just absorb less. They absorb it less quickly. And so a warm ocean absorbs less carbon dioxide more slowly than a cold ocean. And so the carbon dioxide then is it's what persists in the atmosphere, but water vapour, that can just rain out in a day or two. So it's very unstable. So if our planet just had water vapour, it wouldn't stay very warm at all, it would just all freeze out. So that's why, although water vapour is a very powerful greenhouse gas, if we didn't have the carbon dioxide to kind of warm the planet up, then water vapour wouldn't do anything, it would just freeze out. So when people say, we've got all this water vapour and that's what's doing the greenhouse thing, it isn't. You need the carbon dioxide as well to keep it in the atmosphere, to keep the planet warm. So the two work together. I think they're about half and half. I think maybe carbon dioxide is more. I've got the figures somewhere. Anyway, if you look, you see how the carbon dioxide sort of fits in the gaps with the water vapour. You see, there's a bit there and that's a gap, a bit there and that's a gap. That's sort of in the same, but that's another gap. And that is why they're so effective together. If you've got both carbon dioxide and water, there's not really much sort of gap in between the two, where you can get the infrared can actually get through and escape into outer space. Remember, the ground infrared, the ground is warmer than the greenhouse layer, and the greenhouse layer is trapping the infrared, and all it has to do is to trap it, and then it radiates it both ways, into space and downwards. And the magic of it doing it two ways, and it being a layer that does it two ways, because we're just radiating one way, is what keeps the surface warm. And then the question really is, how does it get blocked? But with water vapour, you can sort of see optically, and it's similar in infrared. And as you can see optically, that's a cloud. And you see, if you look like that, it's just these are just tiny, tiny droplets. There's so many of them, and if you keep looking, eventually, then it just is completely opaque. And even though it's not like a sheet of anything. So that's how the water vapour is similar with infrared. Then the carbon dioxide is much more limited. It's very stopping of the infrared, and then sort of people wonder how is it you adding a little bit more carbon dioxide is going to make any difference when it's so opaque anyway. But it's dependent on how, first of all, there's kind of the broadening of the band. It also depends on at what temperature, height in the atmosphere the whole thing radiates into space, and that changes as you increase the carbon dioxide. And so then I just want to talk a thing. You have a negative greenhouse effect in Antarctica. So you would not understand this if you went by the idea of there's something warm up there that keeps the planet warm. But it's got to be cold up there. It's got to be colder than the surface in order to keep the surface warm. Antarctica is so very cold, especially in winter. It's actually, and the air is very dry, and it's colder than and so you have this inversion. It's actually colder than the stratosphere. So actually, the more carbon dioxide you produce in the atmosphere, it actually cools down Antarctica instead of warming it up. So this is another thing. So that's a techie paper about it. As the surface is generally warm in the atmosphere, the total long wave emission of space is commonly less than surface emission. However, this does not hold true for the high elevated areas of central Antarctica. In this region, the emission of space is higher than the surface emission, and the greenhouse effect of carbon dioxide is around zero, or even negative, which has not been discussed so far. And they investigate that in detail, and that an increase in CO2 leads to an increased long wave energy lost to space, which cools the Earth atmosphere system. So, in contrast to the general warming effect of increasing CO2 in other places. So if you have central Antarctica, it's not the round edges, but in the centre of the highest areas of Antarctica, then these are actually centre of Antarctica is being cooled down by the greenhouse effect, which is not what you'd expect. Now, if you went by the non-techie, layperson's idea, which isn't explained properly. And now, this is true, the idea. If you look, so this looks how the temperature anomaly bias from 51 to 1980, and you can see how the Antarctica is just warming up very, very slightly, whereas the Arctic is warming up a lot. There's a little bit of anti-greenhouse effect. Some big ice sheets like Greenland would have a little bit of an effect, and little bits. You get these little inversions happening, and sometimes of the year in the Arctic region. But it's not nearly as strong as in the Antarctic, and it's very strongly, it's actually it's a proper greenhouse effect up there, because it's mainly ocean, and it doesn't have these big high mountains. And and then people want you get this idea, a lot of people think that the reason the Arctic is getting warmer is because of the ice albedo effect. They look at the ice, and they look at and they say, oh, the Antarctica is covered in ice, and the Arctic, it's got these oceans, but it's got the ice melting in summer, and they sort of put 2 and 2 together to make 10 or something, and they think, so that must be why it's warming up so much, because it's got these oceans that freeze in winter, but they're actually melting in summer. And that's the difference between the Arctic and the Antarctica. But that's not the reason at all. And that's called the ice albedo effect. It's actually quite a minor effect, and the world as a whole is actually getting a bit brighter as it warms up because of more clouds. And even in the Arctic, it's getting more clouds in the Arctic as the ice melts. And clouds are a little bit not quite so bright as the water, but they're not that much more absorbing of heat. So the Arctic is a little bit more absorbing of heat, but nowhere near enough to explain this anomaly. And that's not the reason for it. And there's just a slight effect on it, because it's just basically changing water by cloud, and the sunlight is very, very shallow there. Again, even in summer, it's not going in very steep, not like in the tropics. So, and the actual reason is this: if you had a pure water planet with no ice at all, no land or anything, just water, and then you warmed it up, and this is what would happen to the temperature. And you would have a big temperature increase there, and not so much there. And you have big and the smallest temperature increase in the equatorial regions would be say 3, drops down to 2 a little bit high up here, and then in the polar regions it goes right up to 5. So this is a pure aqua planet. And the reason is that as you warm a planet up, then you get more convection. And so more convection, so in the tropics is always the warmest area, because the sunlight hits brightly in the tropics. It's almost vertical there. There's a lot of heat in the tropics, and convection takes the heat from the tropics to the polar regions. So if it weren't for Antarctica, for the solid mass in Antarctica, if you had sort of open sea there, no ice, you don't need the ice, nothing to do with ice. Because we get it warmer up in Northern Europe as well, and it's for the same reason, more convection. We're getting, it's warming up faster in Northern Europe than it does at the tropics, twice as fast, nearly as fast as it in the Arctic region. And the reason is because we're getting more warm air coming from the tropics. As the planet warms up, then the tropics are warming up a bit, but an awful lot of the warm air in the tropics is coming up to Northern Europe and warming us here. And it's not doing nearly so much to, like Australia and Antarctica, because of that big anti-greenhouse effect over Antarctica. And I mean, there may be other effects, but that's at least part of it. And so that's hopefully I understand that a little bit better. And I don't know. This is all kind of quite techy stuff. I kind of have to reread it again to remember. This is the broadening of the bands of the carbon dioxide as you get a bit denser. I don't think I'll go into that techy stuff, but I'm going to talk about some other things. So the effect of the water vapour. So as I said, there are 2 layers of greenhouse gas. There's the carbon dioxide is very high in the stratosphere, and that's like this. You have 2 layers. The outer one is the coldest one, and then you have a warmer one. Then you have the surface, typically, so the lower layer is the water vapour. And so the water vapour is very, very patchy, because I said it just rains out. Water vapour rains out, and air dries. And air dries very easily. And so you can see how it's very irregular for the water vapour. Methane is also very irregular because it's a very short-lived gas. So that's the water vapour, is the lower layer of the greenhouse layers, and above that you have the carbon dioxide. Even though it's opaque down the ground level, but it's right up at the surface is where it does its radiating out, which is where it does its thing, which is what keeps the Earth warm, because it's so high up that the carbon dioxide radiating layer is right up in the stratosphere, and that's what keeps, by being so cold up there, it keeps the Earth warm. So that's the water vapour, and then I just wanted to end with a little bit about describing, this is a genuine greenhouse effect you get in ice. So it's the same idea. It's not just trapping the heat. You get ice melting in Antarctica when the surface is far, far too cold for water to be having melted water. So it's not like a greenhouse effect where it's just trapping it and trapping the heat. There isn't enough heat coming in, but it's the same effect as this. And these are the regions in Antarctica where the left mark is subsurface melt, and that's the surface melt, and the subsurface melt is due to this greenhouse effect again. And so I've got a little diagram, but it's and it also happens on Mars. It probably happens on Mars, and that sort of interests me. So I'll just go back up to here. I don't think I've got a diagram for it properly, so I'll just scroll up to it very quickly. So if I go up to there, it's just like this. So that's the surface ice, and then the sun comes through the surface ice, which is transparent to it, to sunlight. It heats up a layer down there, then that warms up and it radiates the infrared. This goes up to the surface ice, which then radiates both ways, and so that becomes liquid. And so if you go just a half a metre or so below the ice, and you've got clear ice in Antarctica, you'll find a layer of liquid there. And so in clear ice, if you've got clear ice like this blue ice, then underneath the blue ice, if you go deep enough, you'll find liquid water, which is you wouldn't really expect liquid water in Antarctica, but you do. You have this layer deep below the surface of this stuff, and in some of these Antarctic sheets where there's clear ice, and you find liquid water underneath it. And when it's not really warm enough for it, you wouldn't think it should be there. And the same thing should be happening on Mars if it has clear ice. So that's the big thing. So they have found. So see these things here. These may possibly be due to this same solid-state greenhouse effect. So, and what happens on Mars? You get these geysers, which are carbon dioxide effect. And that's, I think, supposed to be frozen carbon dioxide sort of blowing out and landing on the surface. So frozen carbon dioxide on Mars, just as it does here, it turns directly into a gas, quite explosively. And the gas goes and instead of flying up. You can get supercritical liquid carbon dioxide at a depth of, I think, 50 or 100 meters or something. Some depth below the surface. I don't kind of quote me on those figures. I can look it up. But deep enough below the surface of Mars, you do get carbon dioxide as liquid. And you also get carbon dioxide as a kind of liquid. Supercritical is very interesting, actually, because it dissolves organics, and it's different. And the carbon dioxide, it is actually a possible habitat for life, both on Earth and on Mars, a very exotic form of life. We actually have liquid carbon dioxide in our ocean floors. An interesting thing is, if it's deep enough, I can't remember the depth, it's a kilometre, it might be whatever it is, if it's below that depth, then the carbon dioxide liquid actually sinks rather than floating up in the ocean. And so we have great big pools of liquid carbon dioxide below the ocean floor, which haven't been explored, very difficult to study. And it is a possible hypothesis that there could be life there of a different kind from the kind of life that we are. I mean, it's a very way out idea, but if you like thinking, fun astrobiologists like sort of like having fun about these ideas, and there's this idea that there could be life that actually maybe is a habitat for life, and if it wasn't, if life evolved down there, we just simply wouldn't know about it yet, because it's very difficult to study. And so, and that could be, and it's also a possible habitat on Mars. So liquid carbon dioxide, which is a fair bit below the surface, is a possible habitat on Mars. Probably not very likely. I don't think many people would put kind of, you wouldn't bet £1 million or even $1 or two on it having life, but it's a fun idea. And so anyway, but this is solid carbon dioxide, and then the gas sort of flies out like that onto the surface, and it sends up a lot of material. And then later in the year, then that material, and these are flowing out. These little dark spots are the kind of remains of the geysers. And then later in the year, they put these little streaks. See how fast that's moving? I think it's 5 meters a day. They can move very, very fast. Little streaks. And so this is well understood, reasonably well understood, though we haven't got any photographs of them. It's just artist's impression. You just see these black spots form, and it's in the right conditions and the right temperature to be a carbon dioxide geyser. But these seem to be the only hypotheses. So the two of these, there's some in the northern hemisphere of Mars, and the ones in the northern hemisphere of Mars, they form at much lower temperatures. But the one in the southern hemisphere near Richardson crater, the two hemispheres of Mars are asymmetrical, and the southern hemisphere is much higher, much raised up, and at a higher altitude, and and so that's got somewhat different conditions, and for whatever reason this is a little bit warmer there. And it's possible that this is liquid water, cold liquid brines. And the two hypotheses, in fact there isn't any other hypotheses, the two main hypotheses both involve liquid water. And some of the papers, and some astrobiologists, I think, even get a bit confused about this. They think these are both the same thing, and they know the northern one it's far too cold, and it seems that there are other processes involved there. But here, and the only processes here involve liquid water of the people who've researched into this very carefully. And the two possibilities, and one possibility is that this solid-state greenhouse effect is causing liquid water to form below a layer of clear ice, that when these things explode like that, they produce a layer of clear ice, and below that then you get this solid, or not totally clear, but clear enough to produce this solid state greenhouse effect, and then liquid water, and which could originally start off fresh possibly, and then mix up with salt water, and then goes and mix up with the salts that are naturally there on the surface, and they go flowing out, and they may be what's causing these streaks. The only other hypothesis involves very thin layers of I find it a little bit more implausible, but anyway, that you have these very thin layers on the surface of pebbles and things, and just microns thick, and they all combine together to produce enough liquid to go flowing down it's a bit hard to see how that can produce enough liquid to do this. I'm not researcher, I don't know anything, but I'm just a science blogger, but so don't go too much by my intuition, which isn't much of an intuition. It just seems like there's so much stuff flowing down, and flowing so fast, and you sort of think, the solid state greenhouse effect seems like we produce lots of salty brines. The other one, it's a bit hard how it could produce so much. So, but anyway, if you happen to be expert on that, do say. And so this would happen not just there, it would happen anywhere on the surface of Mars, at the polar ice cap, where you have clear ice. And just as in Antarctica, there might well be clear ice there, and we wouldn't be able to tell very easily from the telescopes, from the orbital telescopes. And this would be fresh water, and it's enhanced if there are little dust grains in it. And I do not understand why astrobiologists are not more interested in this. Because the reason is that fresh water is absolutely impossible on the Mars surface, because the atmosphere is too thin. It is possible for a few minutes, but it would quickly kind of it just evaporate. It's near boiling point. In the deeper parts of the Mars, especially in the northern hemisphere, where it's lower, or the base of the Hallis Basin and so on, and the Valles Marineris, then you could have liquid water just briefly, but especially I think base of the Hallis Basin, then you can have it's well below the boiling point of the water, and a few other places like that where it is theoretically stable, but it wouldn't last very long because it's near to its boiling point. It would just evaporate away because it's so warm, but it is theoretically stable. But apart from that, so there might be fresh water there, but not very long lived. And and apparently there's research that hasn't been published yet, that the frosts of Viking, then they can produce, they might be able to produce a few minutes of fresh water on the surface of the rocks in the equatorial regions as they're melting. Anyway, but this is a way that that's the kind of warmest bit. You have little patches of liquid water forming there, just a few centimetres below, and it's at a depth of about 6.3 centimetres. And L here is 11.4. You're talking about a few centimetres below the surface. The ice at this level will melt periodically, and especially in summer can stay liquid overnight, leaving subsurface liquid water in layers of from centimetres to tens of centimetres of thickness. That should happen on Mars, not just in the flow-like features, but almost anywhere, that's me summarising, almost anywhere where there's optically clear ice. So almost anywhere in the polar regions of Mars, you can get up to tens of centimetres of thickness of fresh water. It's quite surprising. And it's trapped from the surface because it's got clear ice above it, which holds in the pressure of the water. And so even you've got a vacuum above, and you have very near to a vacuum, you get fresh water there. And that seems to me one of the most habitable places on Mars, because it's at 0 degrees, and you could have some organics and stuff in there. And I don't know why people don't pay more attention to that. It doesn't seem to get much attention in the astrobiological press. So just these very specialist papers. You hunt around and you find it in the specialist papers, and nobody else seems to mention it. And so that's that. That's my favourite possible habitat on Mars, because it's so cool. It's quite interesting. You would never think you could have fresh water on Mars if you know a little bit of background about how very thin the atmosphere is. But here's where you could do it. You could also have it deep below the surface, and then you have the salty brines over most of it, which is probably very cold, but this is quite warm. And maybe it might have oxygen in it. It would depend on if it was like the effect of the radionuclides on, in it, if that could kind of produce oxygen in it. And yeah, another way you can get fresh water in Mars if you have an asteroid impact. But anyway, that's getting a little bit too far ahead. And I'm not talking about Mars. I'm just talking about the greenhouse effect. And so, yeah. So, but that's just a cool application. It's exactly the same thing. So you've got the temperature coming down, and the surface is much colder. The surface of the ice could be very cold. It would be on Mars, but because of the greenhouse effect, it's a genuine, like not. It's a genuine greenhouse effect in the sense that it's the way the Earth's greenhouse work. I don't know. We don't have a word for it. It's not the way that your polytunnel works or your glass greenhouse works. But it's the way the Earth works. And so you have these cold layers of clear ice, and then below that you have a much warmer layer, and that's kept warm by the way that it radiates heat up, and then this radiates heat both ways, and then keeping it in equilibrium. Then the temperature there is what that should be, and that is like double the temperature because of the layer being separated from it with a gap between the two. And it only works if there's very little convection between the two. If you could have that if you have convection between the two, then it equalized and it just wouldn't work. But you've got almost no convection between the two, and you've got a separate layer that is separated from that is at a colder temperature, then, and that is absorbing of infrared, and then the sunlight going through that layer and warms up the lower layer, and then the lower layer then will stay quite a bit warmer than the surface. And there could be equivalent to multiple layers in between, depending how the trapping works. And that can keep that very warm. And they worked it out. And the polar region, even the extremely cold lunar polar surface above the ice, then you would get liquid water at 0 degrees. Yeah, I think it's quite remarkable. So, there we go. So I'll just quickly do a quick reminder then. So that's the solid state greenhouse effect, which also happens in Antarctica, and it happens on Mars. And then that's the water vapour, which is the lower layer. And then above that you have the carbon dioxide. I've skipped that techie bit. So above that you have the carbon dioxide layer. That is simulating into just one, I think, 2 layers. And then you have the polar. The reason that the Arctic is warm is not because of the albedo effect. That's a minor effect. It is an effect, but it's very minor. It's for the same reason Northern Europe is warm. We haven't got any albedo effect there. It's because of convection. And you also have convection into the southern hemisphere, but then you have that anti-greenhouse effect because the high Antarctic mountains are much colder are actually colder, and sometimes significantly colder, than the greenhouse layer, which means that the greenhouse layer is actually cooling the Antarctica down, because it's warmer than Antarctica, so it's radiating more heat than Antarctica would into space, and so it cools Antarctica down even further. That's the aquaplanet, and then let's look back. That's how this fits the gaps in that. And that's how the 2 layers work. That's how the water vapour, that it's optically thick if you go deep enough. That's like the 2 layers, the troposphere and the stratosphere, lower stratosphere. That is our steel greenhouse thing, and you can work out the temperature of Trantor with the vacuum in between the two if you want. And I've got a little calculation somewhere, but I actually put in the figures for steel, which gets a slightly more complicated thing. You can work out the temperatures for steel. That's again explaining how it works. With a proper greenhouse, it's with the same one, but it's just the same idea. Atmosphere temperature, much colder than the surface. And I explained about how you can have hydrogen atmosphere warming up a very cold planet to such an extent by hundreds of degrees centigrade of Fahrenheit in order to warm it all the way up, so you've got liquid water on the surface. And yet, if you look at this from a distance, then it's the same thing. They would look very, very cold. It would still look like a 30 degrees above absolute zero, because it warms the surface up by being a very, very cold insulating layer up above. And that is the real reason that we have a greenhouse effect, and that is why Earth is warmed up as much as that. So, hopefully this has helped a few of you to, if anybody who watches this, to maybe understand a little bit better how the greenhouse effect works. and maybe clear up some confusions. And there's so many popular articles out there that just get it wrong, and then you get the climate skeptics say, "Oh, the greenhouse effect doesn't work. There's something wrong here," and they're quite right. It is something wrong because it's not being explained properly. So that's what's wrong. It's not that the science is wrong, it's just that the popular explanation of the science is wrong. And so I hope that I can help a little bit by giving the correct explanation.